So most of us would agree that faster than light travel in a vacuum is impossible. The interesting thing is that FTL could be related to time travel into the past, and this is known to cause all sorts of paradoxes and so on. In general, modern physics don't really like that. And then some other scientists come along and say, let's invent tachyons, particles that travel faster than light and can move backwards in time. And we're like, great, thanks. But okay, what's the problem? A few scientists have come up with some crazy ideas. There's still general scientific consensus that doesn't agree with those ideas. On the other hand, it is not uncommon in the history of science for an idea to be initially rejected by the majority, but then to revolutionize science. Maybe it's the same with tachyons. Perhaps we're simply not ready for them yet. Well, in fiction this term has been known for a long time. In Watchmen, tachyons prevented Dr. Manhattan from seeing the future at a certain point. They're mentioned in Dune, in Isaac Asimov's Foundation series, in Star Trek, and so on. Often in Wikipedia articles about some scientific concepts there is a section about the use of that concept in fiction. But tachyons get not just a section, but a whole separate page for this. But still, what are tachyons according to science? What paradoxes are associated with them and how can they be resolved? Can these particles traveling into the past exist, and what attempts have been made to find them? And what is the purpose of studying them for scientists? And what the hell is a tachyonized water that you can actually buy? Today we will talk about all this and more.
My name is Andrei, and this is Cosmos Elementary.
So tachyons are particles, exclusively hypothetical for now, that always, and I emphasize always, move faster than the speed of light in a vacuum.
Tachyons are not just one specific particle. In theory, there could be a whole group of particles under that name. What would unite them is their faster than light travel and certain other properties.
Modern physics and special relativity in particular tells us that nothing can move through space faster than the speed of light in a vacuum. Actually, for anything with mass, not even reaching it is possible, let alone exceeding it. I talked about the speed of light on my channel before and had videos dedicated to it. Usually there are two main explanations in simple terms and without equations why it is impossible for an object with mass to reach the speed of light. One relates to mass. And in simplified terms it goes like this. According to the special theory of relativity, as an object moves faster, its mass increases, and when the object's velocity approaches the speed of light in a vacuum relative to an observer, its mass starts to approach infinity, and to continue accelerating, it would require an infinite amount of energy. And that's a problem because, well, because of infinite energy. The second explanation is related to time. In Einstein's theories, space and time are unified into a single entity, space-time. And we are always moving not only through space, but also through time. Moreover, the faster we move in space, the slower we move in time. While at rest, we move through time at the speed of light. But if we were to start moving at the speed of light in space, then time for us should essentially stop. And that too is a problem.
This is all very simplified, but the main point is that not only we cannot exceed the speed of light in the vacuum, we cannot even reach it.
Particles without mass, such as photons, gluons, and possibly gravitons if they exist, move at the speed of light. From what I've already mentioned, it's evident that mass is the issue for superluminal motion. What should be the mass of tachyons? One might think it should be negative. It does sound very strange. How could something have a mass of -5 kilograms? But physicists use concepts of negative mass and negative energy, and we've even discussed them before in the video about warp drives. I told that, especially in the early versions of calculations for a drive that warps space-time and thus moves through one point in the universe to another faster than the speed of light, negative mass was required. An object with such a mass would behave strangely. And if we were to push it, It would instead be attracted. In some later versions of calculations for warp drives, the requirement of negative mass was eliminated, which made it somewhat more realistic. But with tachyons it's a bit different and even more strange. The hypothesis of tachyons implies imaginary mass. Wait, what? Imaginary mass of an object is the mass that is represented by an imaginary number.
That name might sound weird, but that's a perfectly normal mathematical term.
We won't delve deeply into mathematics right now and explore imaginary numbers, but there's actually a whole playlist of 12 videos about them on YouTube, and if you're interested, I'll leave a link to them in the description. But I'll say that no matter how strange they may sound, we shouldn't dismiss them right away. Even though the word imaginary might make one not take them seriously, but it is more of just a somewhat unfortunate name. For a long time, people only used natural numbers 1, 2, 3, 10, 100, and so on. But at some point, that wasn't enough anymore, and people started using fractions. They also introduced zero and negative numbers.
The same goes for negative numbers. Many mathematicians did not accept them for a long time, questioning how could there be something less than nothing.
Today, negative numbers don't bother anyone, even though they don't seem to reflect anything in physical reality. However, they are very convenient to use, for example, to denote a negative bank account balance.
And imaginary numbers are another extension, and they arose when attempting to solve certain equations.
The imaginary unit is represented by the symbol I, and I equals the square root of -1, or it can be written as I squared equals -1. What is the square root of a negative number? In other words, what number must be multiplied by itself to get a negative result? 2 times 2 is 4, minus 2 times minus 2 is still 4. It doesn't matter if we multiply a positive or a negative number by itself. The result is always positive. So if we take the simplest example, the equation x to the power of 2 plus 1 equals 0 seems like it has no solution, because to have the result be equal 0, x to the power of 2 must be equal -1. And we just saw that it is impossible to multiply any real number by itself to get -1. That's where imaginary numbers come into play. If the appearance of fractions on the number line introduced additional numbers in between, and with the appearance of negative numbers the number line extended to the left, then the addition of imaginary numbers adds kind of a second dimension above and below the line. And again, as strange as it may seem, this is not just a wild idea for the sake of it. Imaginary numbers are now used in certain branches of physics, including quantum mechanics. And ultimately, haven't we imagined all numbers at some point? Well, some would argue against that, of course. As I mentioned, if you're interested in delving deeper into the topic, I'll leave a link to some great videos in the description. For us now, the main point is that tachyons are particles with imaginary mass. The term tachyon was actually coined by Gerald Feinberg. In his 1967 paper, discussions about particles capable of moving faster than the speed of light in a vacuum had occurred earlier, but that's where we see the word tachyon for the first time. The word comes from the Greek word tachy, meaning swift or fast. Considering that special relativity prohibits faster than light travel, Feinberg circumvented this restriction by proposing that these particles arise in a field with imaginary mass. But the concept of particles with such properties did indeed appear before Feinberg. For example, in this 1962 paper, and the limitation that the particles cannot be accelerated to speeds faster than light was suggested to be bypassed by proposing that such particles are born with such speeds. One of the dominant modern physical theories is quantum field theory. Just to remind you, its main principle is that all particles known to us are not simply, as they are often depicted in illustrations, very small spheres or balls. The entire universe is permeated by fields, and at every point in the universe these fields have some value. And particles are nothing more than disturbances or excitations in these fields. Each elementary particle should correspond to its own field. Photons are disturbances in the electromagnetic field, electrons in the electron field, quarks in the quark field, and so on.
Similarly, with tachyons, if there are particles, there should be a field, and vice versa.
In the case of tachyons and tachyonic fields, it's a bit more complicated. The particles themselves are currently only hypothetical. Moreover, in the form in which Feinberg described them, they basically cannot exist. And if such disturbances were to arise in the fields, they would be unstable. However, the term tachyonic field is sometimes applied to a well-known field such as the Higgs field. This doesn't mean that the Higgs boson is a tachyon, and it certainly doesn't move faster than light. Nevertheless, the Higgs field is sometimes described as having an imaginary mass, and in a certain sense, it's referred to as tachyonic.
But let's assume that tachyons exist. If so, they would possess truly strange properties. I've already mentioned faster than light travel, but there are other interesting details.
When talking about tachyons, particles that can only move slower than the speed of light, regular particles, are called bradyons. And also there are particles that always move at the speed of light in a vacuum, loxons, for instance photons. What will happen if we add energy to ordinary matter and particles? This matter will accelerate. Push the cart, it will go faster.
But tachyons should behave in exactly the opposite way. If we add energy to them, they slow down instead. So if we were, let's say, push a shopping cart made of tachyons, it would decelerate.
For ordinary matter, the upper speed limit is the speed of light, and it requires infinite energy to reach it. For tachyons, the speed of light is conversely the minimum possible speed. To slow down a tachyon to measly speed of light would again require infinite energy. And the less energy a tachyon has, the greater its speed. It turns out that the closer the energy is to zero, the closer the speed is to infinity. It's also very strange how a tachyon would appear to us if we could observe it. Due to its superluminal motion, we wouldn't be able to see it on its way toward us. But once it reached us, we would observe the tachyon splitting into two separate images. One of them would depict the tachyon arriving instantly, while the other would show it disappearing in the opposite direction. But let's finally talk about the strangest property: time travel to the past. If a massive object cannot reach the speed of light because it would mean stopping time, then what happens if this speed is exceeded? Does time begin to flow backward? When talking about superluminal motion, the fact that it could lead to time travel to the past is mentioned quite frequently. We can find further explanations through space-time diagrams, light cones, and so forth, but for now the key point is the fact itself. Yes, it is believed that tachyons would appear to move backward in time for certain observers. And this automatically raises various paradoxes associated with time travel to the past. And these paradoxes are among the main reasons why many scientists are extremely skeptical about tachyons. I won't retell the same well-known paradoxes like the grandfather paradox in its regular form. Instead, let's take an example involving tachyons. The problem with time travel to the past is that it violates one of the fundamental principles, the principle of causality. The effect cannot precede the cause. After all, the speed of light is also called the speed of causality. For example, there is an idea of a hypothetical device called tachyonic antitelephone. It's supposed to send signals into the past. Let's delve into a specific version of the tachyon paradox I found in John D. Norton's paper. For this paradox, obviously we first need to assume that tachyons exist, as well as a device capable of emitting and receiving them, and also a tachyon mirror that can reflect tachyons. Let's imagine a spacecraft equipped with a tachyon emitter, and the ship is fully automated. It is programmed to fly strictly along a certain trajectory, emit a tachyon at a specific moment in a specific direction, and react in a certain way to the reception of the tachyon. The numbers 1 and 2 on this diagram represent two moments in time. The ship is flying, And at the point 1, nothing happens. But at the point in time 2, it emits a tachyon which travels and reflects off a tachyon mirror placed in a specific location beforehand. The mirror is positioned to reflect the tachyon which, as we recall, can move backward in time. The tachyon gets reflected and travels further into the past, and again encounters the spacecraft at the moment 1. The tachyon detector on the spacecraft registers the particle at the moment 1. The trick is that we've also programmed the ship so that if the detector registers a tachyon, the ship self-destructs. So at the moment 1, the ship detects the tachyon, then it destroys itself. And thus it cannot continue flying to moment 2 to emit the tachyon. So at the moment 1, the ship does not receive the tachyon and therefore ship does not self-destruct. It can again reach the moment 2, emit the tachyon and then self-destruct at the moment 1, and the cycle continues.
Oh.
From all of this, an obvious contradiction arises. It seems that ship does not receive the tachyon only if it does receive the tachyon. This can also be expressed as if the ship both receives and does not receive the tachyon. This tachyon paradox can be slightly modified if we want to eliminate the need for using a mirror and instead just use 2 ships. However, the essence and the conclusions remain the same. And that's a big problem, especially if one tries to consider tachyons even a little bit seriously. The simplest solution to this paradox is that tachyons do not exist. No tachyons, no paradox.
So, if we were trying to push the boundaries of modern science and trying to build new hypotheses, such a solution would be too radical.
If we still try to entertain the idea of their existence, there's another solution. What if tachyons exist, but we cannot control them? We cannot choose when or how to emit or receive a tachyon, and it all happens purely randomly. If so, then we wouldn't be able to arrange conditions under which this paradox could arise. Also, it is possible that we simply wouldn't be able to distinguish between sending and receiving a tachyon. Another idea is that tachyons do not interact with ordinary matter in any way, and they cannot be detected or observed. In other words, they might exist, but we have no way of knowing or utilizing them for sending signals to the past. These options prevent paradoxes from arising and allow for existence of tachyons. But these are all thought experiments. But what about real experiments and attempts to detect tachyons? After all, if we were to detect a particle with such properties, that would be a completely different conversation. How can such a particle be detected at all? Well, that's not simple to say the least, but there are some ideas. One of the main ones is related to the phenomenon of Cherenkov radiation.
Remember I mentioned that nothing can move faster than the speed of light. Well, turns out that's not entirely true. To be more precise, I always add a caveat: speed of light in a vacuum.
You might have seen news claiming that scientists have already exceeded the speed of light in experiments. In reality, nobody is violating the laws of physics here. In some cases, such articles might be about the following. The maximum speed limit is about 300,000 km per second, but that's in a vacuum. And it's probably not a secret to many of you that when light enters some kind of transparent medium, you might see it slows down. The extent to which it slows down is indicated by a parameter called the refractive index. In my recent video about the speed of light, I provided examples like this one. For glass, the refractive index is 1.5, which means that light slows down by 1.5 times. So the speed of light is no longer 300,000 km per second, but 200,000 km per second. Inside a diamond, light slows down by a factor of 2.5. In that video, I also provided explanations for why this happens and also addressed some common misconceptions, but here's the kicker. Scientists cannot accelerate particles with mass to 100% of the speed of light, but they can accelerate them to 99.99%, and they do this routinely in particle accelerators. And some of these particles, when they are in a medium, do not slow down as much as photons. So it turns out that such accelerated particles in a medium can move faster than photons, effectively faster than light. So in a way, headlines like these weren't lying, but in fact, these particles do not exceed the fundamental limit of 300,000 km per second. Their speed is still below that limit, it's just higher than the significantly slowed down photons in the medium. That's the first point. Furthermore, if these particles are also charged and moving faster than light in particular medium, they emit Cherenkov radiation. And there's an idea that something similar might occur with tachyons. They would play the role of faster particles. In almost a complete vacuum instead of a dense medium, and tachyons might emit Cherenkov radiation. If this radiation is detected, it could indirectly reveal the existence of tachyons. Attempts to do this have already been made, but so far without success. If they do exist, are tachyons new and unknown particles to us, or could they be already known particles? In the second case, neutrinos have been proposed to play the role of tachyons. Several types of neutrinos are known to exist. A vast number of neutrinos are passing through us right now. Currently, neutrinos are not considered to be massless, but they should have tiny masses, and they travel at speeds close to but not equal to the speed of light. There have been instances where claims were made about the detection of superluminal neutrinos. If proven true, they would fit the role of tachyons. In 2011, a group of scientists announced the detection of neutrinos at the Opera detector, a joint experiment between CERN and National Gran Sasso Laboratory, and those particles seem to be moving faster than the speed of light in a vacuum. This story created quite a stir in the media and was obviously met with skepticism by the scientific community. And not for nothing. After a series of checks, it turned out that the anomalous results were due to the equipment defects. So unfortunately, no tachyons here either. There were, of course, other experiments that there is no need to list them all because none of them have shown any confident positive results yet. From the perspective of experimental science, there is currently no data supporting the existence of particles traveling through the universe faster than the speed of light. However, this doesn't stop theorists, and they attempt to apply the concept of tachyons in various fields of physics, astrophysics and cosmology. Efforts are being made to develop the coherent theory of tachyons. They describe the possible interaction of tachyonic fields with black holes, they consider tachyons as candidates for the role of dark matter and dark energy. They search for traces of them in the remnants of supernovae and even discuss the possibility of the existence of such strange objects as tachyon stars.
And of course, such a cool-sounding hypotheses are ripe for use by various charlatans.
Often they try to explain their methods that sound like magic through quantum effects, so tachyons were also used in a similar manner. For instance, how about water charged with tachyons? Miraculous, rejuvenating and all that. Cool. Scientists have been unable to find them for decades, and those folks are already putting them into water. Fascinating. In general, of course, not all scientific hypotheses and theories are always confirmed, which is fine. Not every idea can be right. This is an important part of the scientific process. Perhaps tachyons will never be found, but in the process, scientists could discover many other things, expand the boundaries of science, and in science, even a negative result is still a result.
Thanks for watching. Links to all of the sources are, as always, down below in the description. If you liked the video, feel free to share it with your friends. As you can see, I don't get too many views. And of course, subscribe for more videos in future. Bye.